Hello students, let's look at Newton's laws of motion, specifically the second law of motion. So the question is, what happens to a body when a non-zero net force acts on it? In the previous lecture, in the first law, we discussed what is called the net force acting on a body, and we said that if the net force acting on a body is 0, the body will neither slow down nor speed up. The body will continue to remain in its state of rest or uniform motion, and we call that as inertia. But now the question is, the net force is going to be non-zero. So if there is a net non-zero force acting on a body, what will happen to the body? So to answer that, let us look around us, look at various objects, and then come to some conclusions. So the first observation is, a non-zero net force acting on a body which is at rest will make the body move. I once again repeat, I have a body which is at rest. Now there is a non-zero force acting on the body. So what happens? The body will start moving. The body will start moving, and in which direction will it move? It will move in the direction of the net force. The body accelerates, starts moving in the direction of the net force. Now, let us look at the second observation. You have a moving body. Okay? Let us say the body is moving like this, and you are applying a net force in the opposite direction. A net non-zero force you are applying in the opposite direction. So what happens to the body? The body will slow down, or there is a deceleration of the body. What is deceleration? You know what is acceleration? Acceleration is speeding up of a body. What is deceleration? Deceleration is the opposite of acceleration. There is a slowing down, and I hope you have all studied that acceleration is a vector quantity. So if a body is moving in this direction and it is speeding up, then the acceleration is in this direction. If a body that is moving in this direction slows down, then acceleration or deceleration is in the opposite direction. Okay? Or a body will slow down, a body moving in this direction will slow down when the net force is in this direction. And look at the direction of the deceleration, it is also in the same direction. So this is the observation. So whatever we have observed, I can put it as one single sentence, and that sentence is, when a non-zero net force acts on a body, the body is no longer in equilibrium. The body is disturbed from equilibrium. Now I have a question for you. Can a body which is moving be at equilibrium, or should a body be at rest for the body to be in equilibrium? Try to answer this question. Think about it. I again repeat, when I say that a body is in equilibrium, am I necessarily saying that the body is at rest? Or can the body be moving and still be in equilibrium? Because if you understand this properly, then understanding the laws of motion will be more easy. Okay? So let us try to find an answer to that question. So what is the meaning of equilibrium? We say a body is at equilibrium when the net force acting is 0. So a body which is moving can also have 0 net force. If the net force is 0, it just continues to move with the same velocity. So a moving body can also be at equilibrium. Similarly, a body at rest can also be at equilibrium. So the only criteria for a body to be at equilibrium is the net force acting on it has to be 0. So if the net force acting is non-zero, then the body is disturbed from equilibrium. Disturbance from equilibrium means there is a change in velocity. From 0 it can become non-zero, or from non-zero it can become 0, or from non-zero it can change value to some other non-zero value. So, change in velocity simply means there is a net external force acting, and a net external force acting means there is no equilibrium. I hope the concept of equilibrium is clear to you. Okay, now to understand the second law of motion, Newton's second law of motion, you need to understand a quantity called linear momentum. You know what is linear? Linear means straight line. So, linear momentum. So, again we will try to understand the concept of linear momentum by some observations. You have a wall, somebody is shooting a bullet. You know, a bullet will have a small mass, but it has got a huge velocity. It's got a huge velocity. So, this small bullet, it will come, it will pierce the wall. It will be able to pierce the wall. May not go to the other side of the wall, but it will pierce the wall, right, before it comes to rest. Now, what we will do is take a ball of the same mass as the bullet. Take a ball of the same mass as the bullet. The ball is here. Now, throw the ball. In the first case, it was a bullet. You fired a bullet. The bullet came, pierced the wall. But in the second case, you have a ball of the same mass and you are throwing the ball. Will this ball pierce the wall? The answer is obviously no. The ball will not be able to pierce the wall. The mass is the same. What is different? Why did the bullet pierce the wall? Why did the ball not pierce the wall? The answer is the bullet has a large velocity, but the ball had a small velocity. That is the only difference between the two. Okay? So, this object which came with a smaller velocity stopped easily. Its velocity became 0 easily, but the bullet on the other hand, it comes with a larger velocity. It is even able to pierce the wall before it comes to rest, or it is difficult to stop the bullet. Now, let us look at the second observation. In the second observation, what is happening is a moving truck, let us say there is somebody on the road. A moving truck comes with a certain speed, it is coming with a certain velocity, it hits, let us say, another small vehicle on the road. What will happen? It inflicts a big damage. There is a big damage that it is inflicting on the object on the road. Now, what we will do is, let us consider a car coming with the same velocity as the truck. Now, it is coming and hitting against this object on the road. In which case is the damage more? Both are coming with the same velocity. The truck is going to have a larger mass, whereas the car is going to have a smaller mass. And you find that the truck is able to inflict more damage when compared to the car. So, in the second observation, we are finding that the velocity of both the bodies is the same, but the mass is what is deciding the damage that it is able to inflict. The truck has more mass, therefore, it is able to inflict more damage. Car has small mass, but same velocity, but the damage it inflicts is smaller. Now, let us go back to the first observation. In the first observation, we talked of two bodies with the same mass, but velocities actually decided how much damage it can create. Whereas, in the second example, you had two bodies with different mass, but with the same velocity. You found that the body with the larger mass was able to inflict more damage. So, what do you conclude? You have to conclude that both these are important. Both the mass and the velocity are together going to be important. So, both matter when it comes to seeing how much damage the body is able to inflict. Or what is the meaning of damage? Let me first of all discuss that. So, the ball is there, it is damaging means what? It is not able to stop it, that is why it is damaging, it is able to go in further. Okay. In the case of truck also, the truck is coming with a certain speed, but it is damaging means what? The truck is not able to easily come to a stop. You are not able to stop the truck. That is why it is able to create more damage. Okay. So, you are seeing that two quantities are coming into play in both these examples. One is the mass, the other is velocity. Now, what you can do is, we can now combine these two. We can combine both these quantities, mass and velocity, and arrive at a quantity called the linear momentum. Okay? We can combine mass and velocity and come to something called linear momentum. Let us see why we are doing that. Let us for a minute go back to our two examples. We have seen that mass plays a role, velocity also plays a role. So, based on these observations, first of all, let us look at what is the conclusion we are going to make. The conclusion we are going to make is that the impact or the damage done depends on both the mass and velocity of the body, or the impact is going to depend on one physical quantity which involves mass and velocity. We will combine the two and come out with a new physical quantity called the linear momentum of the body. I again repeat, mass is also causing an impact, velocity is also causing an impact. So, why do not we simply club the two together and come out with a new quantity? So, that new quantity is called the linear momentum of the body. Now, you must remember that when Newton came out with his second law, there was no term called linear momentum. Okay? There was no term called linear momentum. Instead, you know what Newton called it? He called it mass in motion. Mass in motion. So, he is there talking of two quantities. One is the mass of the body, and he is also talking of velocity. So, he says that the motion contained in a body, or the mass in motion decides the impact that a body can have when it is colliding with another object. So, this mass in motion discussed by Newton was later on given this name linear momentum. And I told you linear momentum of a body is going to depend on its mass and its velocity. Now, let us look at the mathematical way the two quantities have been combined. So, by definition, the linear momentum of a body, it is denoted by the symbol small p. Okay? The linear momentum of a body is denoted by the symbol small p, and by definition it is defined as the product of the mass m of the body and the velocity v of the body. The momentum of a body is represented by the equation p equal to m into v. P is the momentum, m is the mass of the body, and v is the velocity. You all know that mass is a scalar quantity, velocity is a vector quantity. Okay? So, let us keep it there. We will come back to this discussion a little later. But right now, understand that the definition of linear momentum is mass into velocity. Thereby, it is considering mass and motion. Now, let us look at what is the SI unit of momentum. What is the unit of mass? Mass is kilogram and velocity is meter per second. So, it is a product of kilogram and meter per second. So, it becomes kilogram meter per second. But at the same time, what you can do is, you just multiply kilogram meter per second, you multiply and divide with second. If you do that, you will get kilogram meter per second square into second. What is kilogram meter per second square is the unit of force, it is Newton. Kilogram meter per second square into second, therefore becomes Newton second. Therefore, your momentum has two units. You can either write it as kilogram meter per second, or you can write it in terms of Newton. You can write it as Newton second, simply because the unit of Newton is kilogram. Newton is the unit of force and Newton is kilogram meter per second square. 1 Newton is kilogram meter per second square. Therefore, the unit of linear momentum becomes Newton second. Yes, now going back, I told you mass is a scalar quantity, velocity is a vector quantity. So, what about momentum? Momentum has to be a vector quantity. You know, the product of a scalar and a vector is again a vector. So, by that argument, momentum has to be a vector quantity. Now, what will be the direction of this momentum vector? You know, a vector will have both magnitude and direction. So, look at that equation again, P equal to m into v. M is a positive quantity, it is a scalar, mass can never be negative, it is a scalar quantity which is positive. Therefore, you can see that P and V will both be having the same direction, or the momentum of a body will have the same direction as its velocity. And if the velocity of a body is 0, the momentum is 0. So, momentum is a quantity, it is a physical quantity that a body will possess only if it is moving. A body which is stationary or at rest will have 0 linear momentum. Okay, now, we talked about momentum. How do you relate net force and momentum? Let us try to understand that. How is the net force acting on a body related to its momentum? So, here I am going to describe an activity, let us call that activity 1. So, in activity 1, look at the figure there, you have a box, obviously it has got a mass, it is on a horizontal surface, it is at rest. So, you want to move it. So, on the left you are finding that you apply a small net force. We have written a small f, small size f, just to say that the force that you are applying is small. So, you apply a small net force and what will happen to the object? The object will start moving. It is initially at rest, now it starts moving. But then you know that it will not pick up a lot of speed. It will not pick up a lot of speed. Therefore, you can say that the acceleration is small. Now, look at the second part of the picture. In the second part, you have the same block, the same mass. But now look at the force that is applied. Pictorially, we are showing the force with a large f, a large f. Large f means a large magnitude force is now applied. So, when you do that, you obviously know that from rest, it will suddenly gain a velocity, or the acceleration that it will get will be larger. But it is the same block that we are talking about. The same block means same mass. For the same block, when you apply a smaller force, you are able to get a smaller acceleration. When you apply a larger force, you are able to get a larger acceleration. Or you are seeing that the net force decides the acceleration. The net force decides the acceleration. Larger the force you apply, larger will be the acceleration that you are able to produce in that body. And mass is a constant in this example. Now, we will go to another activity, activity number 2. In activity number 2, what we are going to do is, we are going to keep the force the same. We are going to keep a constant force. We are going to play with the mass. Playing with the mass means having 2 blocks. So, look at the picture on the left, figure 8. Look at the picture on the left. I have a smaller block. The mass is small. Okay? A force F is applied. It is initially at rest. Now, because of the force that you have applied, it speeds up. There is an acceleration. You note down the acceleration, or you can see the acceleration. Just by looking at that, you can see how much it speeded up. Looking at the final speed, you can say how much is the acceleration. Now, go to the second picture. In the second picture, you are having another block with a larger mass. You can see the size, it is large. But apply the same force F. Apply the same magnitude force F. Let us say 5 Newton. You apply the same force. In this case, you obviously know that it will start moving, but the speed that it achieves will not be great, or the acceleration will be smaller. So, in activity 2, what have we done? We kept the force a constant, but played with the mass. We changed the mass. We found that if you apply a force, when the mass of the body is small, you are able to get a larger acceleration. The same force, when you apply on a larger mass, the acceleration you get is smaller. Whereas, when you go back to activity 1, there you had the same mass, you played with the force, you applied a small force, small acceleration, large force, large acceleration. So, you came to the conclusion in the first activity that force decides the acceleration when the mass is a constant. In the second activity, what did you do? You applied the same force, but on different bodies. When the mass of the body is small, the acceleration you get is larger. When the mass is large, acceleration that you get is smaller. So, let us combine both this. Let us combine both this. When you combine both this, so we arrive at the second law of motion. Before going into the statement of the second law of motion, let me just summarize what we have seen previously in the previous slide. We have seen that a force can change the speed of a body. A force can change the velocity of a body. A force can accelerate a body. So, this is what we have seen. So, now those concepts Newton used, and he arrived at a statement called the second law of motion. So, second law of motion is simply connecting the net force and the change in momentum. Connecting the net force and how the momentum changed as a result of the force acting. Okay, so, let us see the statement. So, the second law of motion says that the rate of change of momentum of an object is proportional to the net force applied on it, and it is in the direction of the net force. So, what it simply means is how much the momentum changed. Momentum is mass into velocity. So, if I talk about a single body, its mass is a constant. So, momentum change means velocity change. So, the velocity change depends on how much force was applied. That is what you had seen in the previous slide. How much force you applied on a body decided how much was the acceleration. And what is acceleration? Acceleration is basically talking about the change in velocity as a function of time. Okay. So, instead of talking in terms of acceleration, what Newton did was he started talking about the change in momentum. He says that a body will suffer a large change in momentum whenever the force applied, the net force applied is larger. When the net force applied is smaller, the change in momentum is smaller. Or he says that it is the force that you apply, the net force that you apply on an object, that will decide the change in momentum. And he writes this in terms of an equation. He says F net is proportional to delta P by delta T. You know what is delta P? Delta P is change in momentum, and what is delta T? Delta T is the time interval. So, he also gets in time, and he says that the force acting on a body will decide how much the momentum will change for a body in a given time interval. Okay, so, that is the meaning of this equation, F net proportional to delta P by delta T. Or he writes it in the form of an equation, and he says that net force acting on a body is equal to a proportionality constant K into delta P by delta T. What is delta P? I simply said delta P is the change in momentum. Mathematically, what is change in momentum? Change in momentum is the final momentum of a body minus the initial momentum of a body. Let us talk about a force acting on a body at a time t equal to 0, and let the force act, and as a result the momentum change, and let us make an observation at a time t equal to 1 second. So, in this time interval 1 second, how much did the momentum change? Initial momentum is there, you know the final momentum also. Change in momentum is final momentum minus the initial momentum. And what is the time? The time elapsed is 1 second. Okay? And k is the proportionality constant. Now, what is k? What will be the value of k? You should know that also. So, what Newton did was, if he designed it in such a way that if the force, momentum and time are considered in SI units, if force, momentum and time are all considered in SI units, then this constant k will be equal to 1, or the equation F net equal to k into delta p by delta t will simply become F net equal to delta p by delta t. And what is p? P is mass into velocity. So, what will be delta p? Delta p is delta mv. Okay? Now, if I am talking of a body, the mass of the body is a constant, then there is no change in mass of the body. Delta m is not there, mass is a constant. Take m out of that delta symbol. So, therefore, F net will become m into delta v by delta t. M is a constant, that is the reason why we are able to take it out. So, it becomes m into delta v by delta t, or delta p is simply because of change in velocity of the body, not because of the mass of the body. The body is having a constant mass, its velocity changed, therefore, its momentum changed. Therefore, F net can now be written as m into delta v by delta t. Okay? And I am sure all of you know what is delta v by delta t. Rate of change of velocity is delta v by delta t. Rate of change of velocity with time is delta v by delta t. By definition, delta v by delta t is acceleration. Okay? Therefore, you can now write this in the form of a new equation called F net equal to mass into acceleration, or whenever a net force acts on a body, it will result in the acceleration of the body. Acceleration is a vector, force is a vector, mass is a positive scalar. Therefore, the acceleration will be parallel to the force that you are applying. Now, finally, let us look at what would be the unit of force. In SI unit, mass is kg, acceleration is meter per second square. Therefore, the SI unit of force is 1 Newton or 1 kilogram meter per second square. So, what do you conclude after this lecture? In conclusion, we are seeing that the net force acting on a body results in the acceleration of a body, and the acceleration of a body will be parallel to the net force applied, and it will be proportional to the net force applied. And if the net force acting on a body is 0, then the momentum of the body does not change. Delta v by delta t is 0, or the velocity of an object remains a constant. So, these are the two important conclusions in this lecture. Thank you.